I studied specifically volcanoes. So this is one of my favorite things to talk about, and I'm so excited to share this with you. So we kind of talked about this is going to be a 3-part workshop. So this first part is really just kind of a discussion. I'll share some visuals that I've prepared, and then the second part is the virtual hike or interpretive hike of a very large volcano in our backyard. So, and then the third activity is going to tie it all together, and we have a really fun
there we go. She's in. It should be just a matter of putting.
Don't worry, I got it.
So to move forward, so let's get started. A little bit about this planet. We live on an active planet. So raise your hand or use the thumbs up feature that Carissa showed us if you've ever felt an earthquake before. All right. I'm seeing a lot of thumbs ups. Cool. Yeah. So especially here in the Eastern Sierra, we get a lot of earthquakes, and throughout the Western United States, we've been getting a lot this summer, which is really kind of exciting. And so that's just showing that the earth is constantly moving and shifting, and sometimes we feel it with earthquakes, but sometimes these earthquakes are so small that we can't feel it, but they're constantly going on. So the earth is constantly moving and shifting. And sometimes we'll hear about a volcano erupting somewhere in the world. So do a thumbs up if you've ever been lucky enough to see a volcanic eruption in person. I have not, so I can't put my thumbs up, unfortunately. No? Okay. Yeah, so these volcanic eruptions are very common. However, they're not as common as the earthquakes that we get. So geologists study the earth to really understand these processes like earthquakes, volcanoes, you name it, that have formed this planet to this day. So by studying past processes like old eruptions or old earthquakes or old landslides, geologists can better understand our active planet, and we can use their understandings to predict how the planet will continue to evolve and change. So today we're going to think like a geologist, and we're going to observe some landscapes to solve the mystery of how these landscapes really came to be. So today we're focusing on a hot topic. It's really a blast to talk about and has lots of good geology puns. Volcanoes. So what is a volcano? Can anyone, we can type it in the chat if you have something to share, and then we can talk about it as we go. But does anyone have an idea of what the definition of a volcano is? If you do, type it in the chat. Or you can unmute yourself and talk about it.
Maybe give a thumbs up if you want to give an answer to that.
Thank you.
Yeah, just so that we take turns.
Yeah. So thumbs up if you'd like to explain what a volcano is. Well, I can help out. So a volcano is when you have an opening in the Earth's crust, and that opening is an easy pathway for magma or molten rock from beneath the crust to reach the surface. So here we are, we live on the surface of the Earth. So a volcano is the opening in the Earth's crust where we live, providing that pathway for molten rock or magma to come to the surface of the Earth. And a volcano can be categorized based on how active it is. So when a volcano is active, it means that it's erupted recently. So within the past 10,000 years. Now that might not sound very recent, but in geologic time, that's very recent, 10,000 years. So it's either currently erupting or has erupted within the past 10,000 years. So did you know that there's about 1,500 active volcanoes worldwide? That seems like a lot of volcanoes, right? So I'm going to share my screen, and I have some cool things to show you. If I can remember how to do this. Okay, share screen. Okay, can everyone see my screen over here?
I can't.
How about now?
Now it's working.
Okay, great. You can see this map right here?
Yes.
Awesome.
If anybody is having any viewing issues, please type it into the chat box and I'll try to help you out. And if you're seeing her screen okay, you can just enjoy.
Okay, thank you, Carissa. Great. So this is a map of the active volcanoes since 1960 to today. So as you can see, they're kind of all over the world here. And again, we said there's about 1,500 active volcanoes worldwide. And this is just showing the active volcanoes since 1960. There's a lot more from 1960 and in the past, within the past 10,000 years, that aren't even on this map. How cool is that? So what about in the United States? Well, this map shows the active volcanoes within the United States. And there's about 169 active volcanoes within the United States. And you can see that they're along this coast and up in Alaska and then along California and along the coast down here. So we do have a few more inland, and these different colors indicate how active they are. So the white and the green means they're not currently erupting, but they're still considered active. And then yellow means that they're pretty active and could be erupting right now or erupted recently. So we see a lot of that more in Alaska and then down in Hawaii. So what about California? Can we do a thumbs up if you live in California? Cool. Awesome. All right, so how many active volcanoes do you think are in California? Do you think, let's do thumbs up for 5. What about 10? What about 15? Okay. What about 20? Okay. What about 100? Cool, yeah, lots of different responses. So actually there's 16 potentially active volcanoes, and 10 of which have erupted within the past 1,000 years. So 10 volcanoes in California have erupted within the past 10 or 1,000 years. That's a lot in just California. And if you zoom in here, I'll provide all these links on our resource list so you can play around on these websites. So if you zoom in to where we are located, you see there's active volcanoes right where we live here. And actually, if you click on these individual ones, we're going to talk about this one, the Long Valley Caldera. But before we get into that, I want to share a little bit more about volcanoes in general. So this is just a fun cartoon that I like to share. So volcanoes are categorized based on how active they are. Now, if volcanoes aren't active, they could be sleeping, which is also called dormant volcanoes. And that just means that the volcano hasn't erupted within the past 10,000 years, and it could become active at any time. So it's just taking a nap, you know, like this one right here, maybe watching some TV instead of taking a nap. And then the other type of activity is when a volcano is extinct. So if it's no longer active and it doesn't expect to become active again. So that's taking a very long nap. So volcanoes, they come in all shapes and sizes. So how about using our video on? Can we show the shape of a volcano that we all think of when we think of a volcano? Let's all do it with our hands. Yeah. We kind of think a volcano looks like this, right? Yeah. So most times volcanoes do look like that, but they come in all shapes and sizes. They can be like this one. This is Mount Shasta in California, Northern California, and it looks just like what we did, like a triangle. However, we could get, oh, this is another example in Alaska. This is Augustine volcano, and it looks like that triangle again. But we can get even more right next to each other. This is in Alaska as well. However, what about this? This isn't the volcano. This is the volcano. So this looks a little different than what we envisioned, right? Does anyone know if we live near this volcano right here? Let's do a thumbs up. Does that look familiar at all? Yeah. So this is on your way from Mammoth up to June Lake. This is the Glass Creek Dome. And it's a volcano, and it's an active volcano. It hasn't erupted for some time now, but it's considered active. And it is shaped different than what we think when we think of a volcano. Now, what about this one? Has anyone heard of Panum Crater? Thumbs up. Yeah, that's just south of Mono Lake. So this, when you're looking at it from the ground, it kind of just looks like a hill. But when you look at it from the air, it has a very interesting view. It is a crater with kind of this dome inside of it. But it's not that iconic triangle that we think of. So when we look at more, what about this one? This is the volcano that I'm pointing out right here. And this is nearby as well, but it's not very big. So volcanoes can come in all shapes and all sizes. Now, the actual physical appearance of the volcano, so the size, the shape of it, tells us a lot about the volcano. Specifically, what type of eruption occurred to actually form that volcano. So, the type of eruption is influenced by the composition and the characteristics of the magma within the magma chamber. So let's talk about magma. Here, I've drawn a little cartoon, and this is our magma chamber, which I like to call the magma house. It's where the magma lives. And magma is essentially molten rock, which means that it's melted rock. Now, does anyone know the temperature that water boils? It's kind of a harder question. Maybe the parents can help out with that one.
Give your thumbs up if you have the answer. We'll call on you.
Yeah, what temperature does water boil? If you have a thumbs up.
Is that Dory?
360 degrees
Okay.
Fahrenheit.
That's close, yeah.
Tori, do you want to give a try too?
Yeah,
Did you
go
have
for
it? Is that Clinton? Sorry, I think we're unmuting you at the same time. I'll let you do it.
Yeah. It's 100 degrees.
Yes. Yeah, so
Yeah, Celsius.
Celsius, exactly. So 100 degrees Celsius. Now, that's about 212 degrees Fahrenheit. Okay, so keep those numbers in mind as we talk about magma. So magma is made up of three main things. It's made up of a melt, or a liquid. It's made up of minerals, or those crystals, and those are our solids. And then bubbles, which is the gas. Now, so for minerals to actually form from a magma, it's when the melt is cooling down. So let's say we have a hot magma. Here we see it's about 1200 degrees Celsius. Now we said water boils at about 100 degrees Celsius. So this is some really hot magma, right? So in order for crystals to form, the melt of the magma, the liquid of the magma, has to cool down in order to crystallize a mineral. So let's say our melt is cooling down, and it crystallizes a mineral. Well, that's not all that happens. When you crystallize,
Sorry.
it's okay. You also release some dissolved gases. And these gases could be water vapor, it could be carbon dioxide, it could be sulfur. So when you're crystallizing a mineral, you're also dissolving a gas into the magma. Pretty cool, huh? So if a magma is really, really hot, it's hard for a lot of crystals and a lot of bubbles to be present because it's too hot for them to crystallize. Does that make sense? Yeah? Okay. So here, with our hot magma, we have more melt or more liquid present. We have less solids or less minerals, and we have less bubbles or less gas. So let's go to a cooler magma. Now, when I say cooler, I'm talking about 850 degrees Celsius. We're still much higher than water boiling, right, at 100 degrees Celsius. But this is considered a cooler magma. So when you have a cooler magma, you're going to have a lot more crystals and a lot more bubbles present because it's cooled down, and those crystals can crystallize and those bubbles can dissolve into the magma. Does that make sense? Yeah? Okay. So with a cooler magma, as this magma is cooling down and cooling down and cooling down, you're going to get more and more crystals forming. So it turns into kind of this mushy mixture where you have much more minerals or solids, more bubbles or gases, and a little less melt or liquid. So it's kind of like a slushy more than like water. Does that make sense? Okay, we're getting there. Cool.
I like the slushy instead of water. That was helpful.
Okay, wonderful. I mean, my favorite thing is to compare geology to food. It works every time. So let's talk about when this volcano wakes up. So right now it's sleeping, and let's say it wakes up. So when an eruption is about to happen, the magma rises from the magma chamber, and it rises through this thing called the conduit. I like to refer to it as the volcano elevator or the magma elevator. So it brings the magma from deep below in the magma chamber up towards the surface of the volcano. And where the magma is erupted to the surface is called the vent, which is the opening in the Earth's crust. So let's say our magma is that really hot magma that has less crystals and less bubbles. What do you think it's going to form when it erupts? It forms a lava flow. So when magma erupts to the surface, it gets a new name, and that's lava. So lava is erupted, and it forms this nice, probably slow moving lava flow. It's very fluid. It kind of flows like honey. So think of honey or your maple syrup that you put on your pancakes. Yeah, so it kind of flows more like honey or maple syrup as a lava flow. However, if we have that cooler magma that gets erupted and it has a lot of crystals and a lot of gas in it, it forms, instead of a lava flow, initially, it releases all of those gases that it contained in the magma chamber. So when you release all those gases, you form this really big, it's called an eruption cloud. And we have some videos that I'll show you that shows some really great ones. And an eruption cloud goes high up in the air, and what happens in the magma is when the magma explodes out of the vent, it just rips apart. Instead of forming a lava flow, the magma rips apart, and it forms ash particles. It forms rock fragments that are just thrown into the air, into this eruption cloud. And sometimes, so the eruption cloud is full of that ash and rock fragments, and that's called tephra. So I'm going to say that word a few times, tephra. So it's just that ripped up magma that's rock fragments now, and then into these smaller particles called ash. So when a eruption cloud goes high up in the air, it can also collapse down the side of the volcano. And that's called a pyroclastic flow. And pyroclastic flow is an interesting name. It's a Greek word for hot ash cloud, pretty much, or hot fire cloud. So when you hear pyroclastic, you're thinking this very hot, fiery cloud. So
That's a good word. I'm going to work that into my regular vocab, pyroclastic.
Yeah. It's really exciting. It's an exciting word. So sometimes you can have, if there's a lot of gas present, you can get an eruption like this, causing a pyroclastic cloud, pyroclastic flow, but then you can also get a lava flow. So you can get both these types of eruptive products, we call this. So this is an eruptive product, the lava flow. It's a product of the eruption. And then you can get a pyroclastic flow, which is another product of the eruption. So I'll go into that a little more in more detail. So really understanding the characteristics and properties of the magma itself, pretty much how much crystals and how much gas is present, you can learn so much about what type of volcanic eruption and what will be erupted, which leads us to our two main categories of volcanic eruptions, which are non-explosive. So non-explosive eruptions are also called effusive eruptions. And these are those, this is when you have that hot magma with less crystals and less bubbles. So when it erupts, it forms these nice long lava flows, and it runs like that honey and that maple syrup that we can think of. So I have a fun little video I'm going to show you now. Everyone can see this, right? Okay, great. Just going to watch about a minute of this. This is a non-explosive eruption. Can everyone hear it okay?
Give a thumbs up if you can hear the video okay.
It erupts from volcanoes.
Great.
It can erupt from the volcano's summit or from its slopes. Lava flows come in a whole variety of shapes and sizes. Some lavas, called basalts, are runny, like honey. They can flow quite easily and sometimes form red-hot rivers, like those seen in Hawaii.
I think I would become a volcano expert.
Which can generate rapidly moving lava flows. Basalt lavas usually move at around walking or running speed, but they can be faster. Lakes of lava can also form, where lava pools. Basalt lavas normally travel for just a few kilometers, but can flow for tens of kilometers during big eruptions, or when enclosed rivers of lava are formed. These are called lava tubes, which keep the lava hot and fluid so it's able to travel further.
Okay, so those are some pretty spectacular videos of lava flows, right? And I'm going to provide all these sources for you to come and you can watch the rest of this on your own time. So those are some great examples of these non-explosive eruptions. Now what about explosive eruptions? So explosive eruptions is when you have a lot of crystals and a lot of gas present, and when it's finally able to erupt, it does so very explosively. So that kind of ties in with that cooler magma with more crystals and more bubbles, right? More gas is present. When you have more gas is present, you're building pressure within the volcano. And then when you're finally able to erupt, it erupts very explosively. And the magma is torn apart when it erupts. and it rises through that conduit, reaches the vent like here, and then it escapes as this tephra or volcanic ash column and cloud. And it forms this cloud full of ash and rock fragments. So I have another fun video to show you about explosive eruptions.
Magma is the molten rock beneath volcanoes. It's filled with gas that expands as it erupts, like the bubbles in a fizzy drink when a bottom. In explosive eruptions, this tears the magma apart and shatters solid rock. These explosions form fragments of magma and rock, which range in size from a fine dust to boulders the size of cars. The finest
Weather is changing all the time. That's why this is so important.
rocks thrown from a volcanic vent are sometimes called volcanic bombs. The biggest rocks fall to the ground close to the volcano.
Okay. So those are some pretty spectacular videos of explosive eruptions, right? So I went, let's talk about this really fast. So here's an example taken from Mount St. Helens. So this was also Mount St. Helens, the eruption in 1980. So this erupted in 1980, and then it was pretty active until about 2007. So this photo was taken, I believe, in about 2004. And this shows the eruption cloud going really high up into the atmosphere, but then some of it can collapse and travel along the volcano, which is that pyroclastic flow that we'll be talking about. So I did my own little experiment to test out these different types of eruptions. And I have a fun little video to show you now. I'll try to make it bigger. Hey everyone, we're going to do a quick demonstration to show how non-explosive eruptions and explosive eruptions behave once they erupt and what they produce. So before we do any science experiment, make sure you have your protective equipment, like my apron, with non-explosive eruptions, the magma is almost too hot to have too much crystals and bubbles present within the magma. So when it erupts, what do you think happens? Well, let's use maple syrup to see how a lava flow from a non-explosive eruption happens. So it flows easily down this plate. I turned the sound off on purpose because there was a lawnmower. That flowed easily as a lava flow, almost like honey or maple syrup. So you can think of it in that way. Now, what about explosive eruptions? Well, okay, so with explosive eruptions, let's see what happens when you have a lot of crystals and a lot of gas present when it erupts. Are you ready? Okay. An explosive eruption.
I will get to that also.
Your protective equipment because it gets messy. All right, so that was just a fun demonstration that everyone can try at home. I recommend doing it outside because it does get pretty messy. So now that we've kind of talked about the types of volcanic eruptions, let's talk about the three main types of volcanoes in order of how explosive they are. So starting with shield volcanoes. Thumbs up if you've ever heard of a shield volcano. Thumbs up. Cool. I see a few thumbs. Awesome. So a shield volcano, it erupts non-explosively. And the reason we know this is because it forms these very broad, very, very big volcanoes, but they're not those steep-sided volcanoes that we think of, right? So these are common like in Hawaii, and you get those long lava flows that can travel very long distances, but very non-explosive eruptions. Now, what about stratovolcanoes? So a stratovolcano essentially is that iconic triangle-shaped volcano that we think of when we think of a volcano. And strato just means layers or layering. And what it describes a volcano perfectly for a stratovolcano, because as it erupts, it's building those eruptive layers and getting the taller and taller and bigger and bigger. So strato means layers of old erupted material that have solidified and hardened to form those rocks. Pretty cool, huh? So this is an example. This is Mount Hood. This is actually the volcano that I studied in graduate school, so it's near and dear to my heart. Mount Hood is a stratovolcano. This is Mount Hood seen above, and that's Mount Jefferson behind it. Now, I know most people have heard of this next volcano. Does anyone know what volcano this is? I'll give you a hint. This is also the same volcano on the right side. This is Mount St. Helens. So Mount St. Helens is shown here on the left side before that 1980 eruption. And you see that it's that beautiful cone shape like that. And then when it erupted in 1980, it had a lot of that gas built up within the volcano, and it blew its top, and it took out most of the top of the volcano and left a huge crater behind. Now, this is a great example of a volcano that erupted and formed pyroclastic flows, but also it had some lava flows. So with stratovolcanoes, that's that kind of volcano where you get lava flows and you get eruption, ash clouds and pyroclastic flows. So you kind of get a mixture of both. And usually it starts out with a very explosive steam and gas and ash eruptions, followed by lava flows later on during the eruption process. That's pretty cool. So moving to our last type of volcano, which we're going to focus on for the rest of this workshop. They're called calderas. So thumbs up if you've ever heard of a supervolcano. Yeah? Oh yeah, I see lots of thumbs. Great. So a supervolcano is the most explosive eruption you can get. And when you think of a supervolcano, most times you can't even tell that there's a volcano even there, which we're going to talk about in the next part of this workshop. So right here, this is Crater Lake out in Oregon, and it forms this huge crater, and it has a crater lake within the crater, hence its name. So when you have this big depression or empty hole, over time with enough rainfall and snowfall, you could develop a crater lake within the caldera. Now, thumbs up if you've ever heard of Yellowstone. Okay, I see some thumbs. Cool. Yeah, Yellowstone is a very well-known supervolcano. Now, thumbs up if you've ever heard of a supervolcano here in our backyard in the Eastern Sierra. Okay, I see some thumbs. Yeah, so we do have a supervolcano right here, right outside of Mammoth Lakes, and it's less known than the Yellowstone caldera because it's only erupted one major time, whereas the Yellowstone caldera erupted at least 3 major times. So that's why it's more well known, and it's a national park. So I have this fun video here. I didn't download it. Here we go. And it talks about how calderas actually form. Okay. Another fun experiment.
Hi, I'm Dr. Dina. I work with the U.S. Geological Survey in Menlo Park, California, with the Volcano Hazards Program. Today we're going to talk about calderas. When most people think about volcanoes, they think of a triangle shape, and that's what many volcanoes look like. But there are other shapes too, and one of those is called a caldera. What we've done is created a simple experiment to show how calderas form. The experiment uses flour, a piece of tubing with a balloon attached at the end, and a bicycle pump. So what I want you to imagine is that this is the surface of the Earth in an area that's volcanically active. Underneath the surface of the Earth, we're going to inject some magma. When we inject the magma using our pump, it's going to push the surface up. So let's watch. As you can see, the flour is being moved out of the way as we inflate the balloon or add magma to the system. The Volcano Hazards Program has monitoring equipment at different volcanoes to watch ground deformation such as this. In this case, what we're going to do is we're going to pretend that this large amount of magma erupts. To do that, I'm going to let the air out of the balloon, and then we're going to watch to see what happens. So as the air comes out of the balloon, you want to imagine the magma escaping from the magma chamber. Once the magma leaves the magma chamber, there's nothing to hold up the overlying rock. And so all that rock collapses down to where the chamber used to be. So you can see in our experiment, the flour has now collapsed in a somewhat circular shape. We call this shape a caldera.
So I just love that experiment because it shows so well what happens when a caldera forms. So a caldera essentially is just a big hole in the ground. And it's a big hole because it erupted so much magma that it left this vacant space beneath the surface of the Earth, where as soon as it gets erupted, all that magma is out of the crust of the Earth. What do the top of the rocks do? They have to just fall and collapse in, and then you have this crater or hole in the ground. So we're going to transition now to part 2 of our workshop, and we're going to dive into the supervolcano in our backyard. But before we do, I want to open this up to any questions that anyone might have of anything we talked about so far.
I haven't received any questions so far, but we can give a minute or two if anybody wants to submit one. I really appreciated that video. I was telling Molly before we started, I'm just going to chat and fill the space in case someone needs some time to type their question in. But I have a really hard time with learning about the Earth when geologists tell me, because it's over so much time period that I can't visualize it. So I also really appreciated that flower demonstration. That helps me better understand what a caldera is.
Oh, that's really good to hear.
Yeah, thank you for including that. So we do have a question from William, who's actually downstairs here in the library today, and he has asked, where is the Mammoth caldera?
That's a great question, William. I'll kind of cover that in the video that I'll be showing, but this this picture right here, you can still see my screen, right?
Yep.
So this picture, I'm just going to zoom in on this, because this,
Oh.
see here it says Mammoth Lakes, and this is Mammoth Mountain, and this circle that I drew in here, that is the Long Valley Caldera. So when you asked about the Mammoth Caldera, I'm not sure if you meant this caldera, the super eruption that we're going to talk about, or Mammoth Mountain itself is a volcano. But instead of having a hole in the ground like a caldera, it's considered more of a stratovolcano, but really it's just different eruptions that have built itself up. I think about over 50 different vents or eruptions forming these limbs that have kind of just mushed together or coalesced together to form Mammoth Mountain. So it doesn't really fall within the shield stratovolcano caldera categories. In between stratovolcano and caldera is called a dome forming eruption. That's really sticky lava like toothpaste that comes out of the vent, and it just kind of builds itself up, and it's pretty explosive, but more or less just kind of builds a dome of lava and then stops, and then continues and builds another dome and then stops. So over time, Mammoth Mountain has just built all these different domes that have come together as one main volcano.
I have a question. No one else submitted a question yet, and I have to step out again to check on some of other kids here working on other stuff. But is it common that like for these different types of volcanoes to be located so closely together? Does that occur elsewhere, or is that pretty unique to the Mammoth area?
So that's a great question too. So oftentimes you do have volcanoes that are close to each other. Here it's special because this whole volcanic system of the Eastern Sierra, it shares one main magma reservoir. So we talked about magma chambers, which is also called the magma house, where the magma lives. A magma reservoir is a much larger magma chamber. So a magma reservoir can feed individual magma chambers. And so for Mammoth Mountain, it's thought that it's related to the Long Valley Caldera system because it shares possibly the same magma reservoir, but has different magma chambers coming off of that magma reservoir. That's a much more complex question, but a very good question.
Thank you.
Yeah. Does anyone else have any other questions?
I don't see any more questions.
Okay. So without further ado, I put together this interpretive hike. So I don't know how to make it so big. Here we go. Of the Long Valley Caldera. So we're gonna talk all about the Long Valley Caldera now. So this video is about 16 minutes long, and I'm just gonna show it throughout, and if you have questions along the way, feel free to write them in the chat, and then video's over, we can answer those questions. Does that sound good?
Yeah, thanks. I'm excited. This is my first virtual hike. It's my first interpretive hike too.
Oh, yay! It's really fun, so I hope everyone likes it. Here we go. Here I am overlooking the Long Valley Caldera just outside of Mammoth Lakes, California. Now, it's kind of hard to tell that there's even a volcano located right behind me, right? Well, let's zoom out and look from above. Okay, how about now? Can you see it? Now, just behind me, we can see part of the caldera that formed after the huge eruption that happened about 760,000 years ago. Now, this oval-shaped caldera is about 20 miles long and about 10 miles wide. Now we know that it's a caldera, a really big one in fact. So what type of eruption caused this caldera to form? Do you think a non-explosive eruption or a really explosive eruption? That's right. This caldera was formed from a very, very big explosive eruption. In fact, about 650 cubic kilometers of magma was erupted explosively caused during the collapse of the caldera forming eruption. Now, 650 cubic kilometers of magma, let's think of that in terms that we can relate to. So that's about the same volume as covering the entire state of California in 4 to 5 feet of erupted material. This yardstick is about 3 feet tall. Now 4 feet would be to here, and 5 feet would be to here. Almost as tall as me. I'm about 5 feet and 1 inch. So about as tall as I am of erupted material covering the entire state of California. Now that's a lot of material. And the hole, the caldera that was left behind just after the eruption, the hole was about 2,500 feet deep. That's a really big hole, and it had no outlet. So over time, a caldera lake was formed in the big caldera hole. And this happened over the course of about 600,000 years for this lake to form. And just about 150,000 years ago, the lake level rose so high that it spilled over the caldera and it rushed down the only outlet it could find, which happened to be the Owens River Gorge, what we know the Owens River Gorge is today. So the Owens River Gorge was cut by the overspilling of the caldera lake that rushed down to Bishop, California. And in fact, Crowley Lake, right behind me, is the leftover caldera lake. How cool is that? So what do you think was erupted? Do you think the magma had less crystals and bubbles, which formed a slow-moving lava flow, kind of like that maple syrup demonstration we saw earlier? Or do you think the magma had lots of crystals and lots of bubbles, causing the magma to rip apart as it was erupted, forming a fast-moving pyroclastic flow, similar to that soda demonstration? Yeah, you're right. This is a very explosive eruption, which means that the magma had a lot of bubbles in it, or gas. So when the eruption occurred, it was extremely explosive and ripped apart that magma, forming an ash cloud that went up about 10 kilometers high in the sky and then later collapsed, forming flow deposits going on all directions within the caldera. So what happened to all that magma and the pyroclastic flow deposits that were erupted? Well, that's a great question. Since the pyroclastic flow deposit collapsed and stretched out across the world, it also kind of filled in that huge hole, that 2,500 feet deep hole caldera that we talked about earlier. So about half of the total erupted material about a third of the pyroclastic flow deposit flowed out in all directions. Bishop Tuff. Flow deposit in this caldera. I'm gonna jump in. If you're not muted, can you please mute your microphone? Okay. I just want to make sure everyone can hear. depression or the caldera. What about the rest of it? Well, about a third of the pyroclastic flow deposit flowed out in all directions, forming the Bishop Tuff. This is the pyroclastic flow deposit that we refer to from this caldera forming eruption at the Long Valley Caldera, the Bishop Tuff. And the Bishop Tuff blanketed the whole landscape and covered everything in its path. There were no more gorges. There were no more river valleys. There were no more mountain ridges. It covered everything in its path, and we'll show an example of it in our next stop. Now, a sixth of the erupted material was dispersed across the North American continent. And the way it's dispersed is because it's composed of small ash particles. Now, ash is smaller than a sand-sized particle, smaller than what I'm holding in my hand right now. And it's made of volcanic glass, and it's easily transported through wind patterns. So it traveled across North America and is dispersed as far as Kansas and beyond. Now we'll see an example of that on our other stop that we'll see. Now the Bishop Tuff blanketed about twice the area that's exposed today, and it stretched across as far as the Mono Basin up north and as far south as Big Pine. Now today, it's either buried or has been transported or eroded away over time. Okay, let's go look at the Bishop Tuff in more detail and other materials that were erupted so that we can investigate more and more about this eruption. Let's go. Welcome to the Owens River Gorge. Here we can see inside the layers of the Bishop Tuff. And I'm standing on some boulders of the Bishop Tuff right here as well. So what is tuff? Well, tuff is a type of rock that's formed from a pyroclastic flow. When the pyroclastic flow deposit is so hot, it fuses the individual ash particles that's composed of volcanic glass. They're fused together, which we call welded. So the Bishop Tuff is a welded tuff. And that just shows how hot this flow was when it was deposited. Now, there's some other rocks that we could find within the Bishop Tuff, and they're called pumice. Has anyone heard of pumice before? Well, pumice is a type of volcanic rock that's formed during very explosive eruptions, like the Long Valley Caldera eruption forming the Bishop Tuff. And pumice is made primarily of volcanic glass that's welded together, but has individual holes throughout the rock, and it's made up mostly of gas. So when it's erupted, the gas escapes, and you're left with a frothy, very light rock. Now within the Bishop Tuff, there's also a lot of rock fragments that have been picked up along the way when this flow is moving across the ground surface. And the rock fragments can be all different rock types. It depends on where you're located from the area, which is really cool to think about. So when the eruption occurred, it exploded the surface of the ground where the caldera formed, and it incorporated the previous rock that was there into the pyroclastic flow. So here we're on the south end of the caldera, and we see a lot of these black inclusions of these rock fragments. And they're thought to be a type of mudstone that's commonly found up near Mount Morrison near Convict Lake. So that just shows the power of this caldera, where it ripped apart the ground surface and then carried that rock that it ripped up down through the flow towards Bishop, which is right behind me. So depending on where you're located near the caldera, you'll find different rock fragments within the Bishop Tuff. So here we have mudstones. Up north, you might have granite pieces within the Bishop Tuff, and you might find some quartzite too. Now let's take a closer look at this Bishop Tuff. We can use our observations that we make as clues to investigate even more detail about this eruption. So let's get started. Now, one observation that I make is the color of the rock itself. It's kind of a pink orangish color. And the black that you see is a form of lichen. And here are some examples of the pumice that we find within the Bishop Tuff. So these are individual pumice fragments that, similar to these rock fragments, got picked up along the way as this pyroclastic flow is moving across the landscape. And it picked up anything in its path and included it within the pyroclastic flow deposit, which solidified into this Bishop Tuff. We're at the toe end of the Bishop Tuff. Now remember, we talked about the full extent or how far the Bishop Tuff traveled when it was first erupted. And it's thought that it traveled all the way down to Big Pine, past Bishop, which is just south of us right here. And over time, the Bishop Tuff has eroded or been transported away through different forces like glacial activity, rivers, wind, you name it. This eruption happened about 760,000 years ago. So a lot of changes have occurred since then. But today, this is the location of the toe of the Bishop Tuff. And as you can see in front of me, and also right behind me as well, is the greatest example of the ash flow layers that are accessible to us here. And this is the Chalk Bluff Road, and you drive right past this layer, these layers of the ash flow, and we're going to take a closer look at them. So ash, volcanic ash, is smaller than the size of a sand particle. So here I have it broken up into smaller pieces, and as you can see, it just kind of leaves behind this fine dust. And this fine dust can be transported very far distances through wind and air transportation. Great job, geologists. So now that we've discovered more and more about this volcano and the super eruption that occurred about 760,000 years ago, we can use our observations to think about how this eruption and other eruptions similar to this one impacts nearby communities, like the one right behind me, the town of Mammoth Lakes. So volcanoes are very dangerous, and geologists monitor the volcano's activity daily. The volcano has been sleeping for some time now, and if it ever decides to wake up, which likely won't occur in our lifetime, they have safety measures to alert the public and plans to keep everyone safe. For more information, you can go to the California Volcano Observatory website, which I'll provide a link to. So some very positive impacts on the community that we have today are geothermal energy, and located right behind me is the Casa Diablo Hot Springs and Geothermal Facility, and it's located just outside of Mammoth Lakes. So this power plant taps into the Long Valley hydrothermal system. What does hydrothermal mean? That's another great question. Well, hydro means water, thermal means temperature. So it's hot water that's located underground, not too deep, around our water table level. And the thermal energy from that hot water can be transferred to drive generators that produce power. How cool is that? And the power plant behind me produces enough energy to power over 40,000 homes in the Eastern Sierra. So if you live in the Eastern Sierra, your power likely comes from the hydrothermal system of the Long Valley Caldera. Some other positive impacts to the community of this volcano are hot springs. I mean, who doesn't love nature's hot tubs, right? And there's many hot springs that are all natural throughout the Eastern Sierra, and that has to do with the Long Valley hydrothermal system. Another positive impact to the community are rich soils. So when volcanic ash mixes with soil, it provides a lot of nutrients. And these nutrients are great for farming and producing a really nice crop system here in the Eastern Sierra. So some really great positive impacts on the community. Yes, volcanoes are dangerous, but when they're sleeping, they can provide great positive impacts to our community. All right. So
I'm going to give you an applause for that, Molly. That was awesome. Thank you.
Yeah, it was really fun to make. Okay, so I'd like to answer some of those questions now. I see a few of them.
Yeah. Jennifer, would you like to unmute yourself and ask yours? If you don't, we'll just read it.
It's fine. I have my kids are going crazy. Basically, we were just up there. We go up there for camping. We live in Riverside, so we live farther away from you guys. But at June Lake, is there a chance that you can find some pumice stone and stuff? Because like we were looking for rocks to skip at Convict Lake and June Lake, and one of my cousins actually found one. And they're like, look at sinker float, let's see. And it was floating. And I was like, that looks like pumice stone, but I don't know if it's pumice stone. And then we weren't sure if it was just dried up species or what it was. So that was why I was like, oh, there is pumice out there. So maybe that was it. I don't know.
Yeah. Well, that's a really good observation to make, especially I wanted to point out how you threw it into the lake and it floated, right? So that's how you can tell if it's pumice, because it has so many holes in it that when you throw it into a lake or water, it floats. So yes, that pumice likely either came from the Long Valley Caldera eruption or from eruptions that occurred in the Inyo Mono volcanic chain, which has been more active recently. So it's actually the youngest volcanic chain in North America, which is, if we had all day, we could talk all about the amazing volcanic activity here in the Eastern Sierra. But likely near June Lake, and there's a lot of pumice that has been erupted from both the Long Valley Caldera and the Inyo Mono volcanic chain. Yeah, great question.
That's a good observation. I didn't know that about pumice. That's interesting.
Yeah.
So, I had a question as well, and if anybody else has one, feel free to shoot them in the chat box now. I'll take up a bit more time posing mine, but I'm realizing after listening to a bit more detail about that Bishop Tuff, when you started off saying what was there from the Long Valley Caldera eruption, you said there was 5 foot of something over the whole state of California?
Well, so so the total eruptive material that was erupted during the Long Valley Caldera eruption was about 650 cubic kilometers of material.
I see.
That just sounds like so much material. So I did a rough estimate of the area of California based on the volume, and that comes out to be anywhere from 4 to 5 feet if you cover the entire state of California.
Thanks. That was a spatial example. I see. So it flowed probably down past Big Pine, but if we were to spread that out over all of California, it would have been about 5 foot of eruptive material over the whole state. That's wild.
Yeah, so the pyroclastic flows spread up towards Mono Basin, down south to Big Pine, and half of the material actually filled in the caldera. And that's why we don't have that really thick, we don't have that big hole anymore, pretty much. And about a sixth of the material was ash, and that is easily transported by wind and through air travel. So that was dispersed throughout the North American continent. But if you took all of that eruptive material and spread it out evenly, it would cover the state of California in about rough estimate of 4 to 5 feet.
Wild. Okay, cool. Thanks for that clarification. Well, I don't see any more questions, so I guess we're ready to move into section 3.
Okay. So section 3 is a fun activity for everyone to do. And if we have time after, whoever would like, I think we'll have plenty of time after. Whoever would like to share what they did for their activity, that would be wonderful. So you can still see my screen. So in the email that was sent out earlier in this week, I believe we had this worksheet attached. Yeah. So this activity is to highlight that, yes, there's many types of volcanoes, and volcanoes share very similar and important features to actually make them volcanoes, but all volcanoes are unique. And as people, we all share similar features, but we're all unique in our own way, just like volcanoes. So this activity is called I'm Unique Like Volcanoes. So you can either use this worksheet that I provided, or you can freehand or draw your volcano as I go through, and I'll draw my volcano on a blank piece of paper here. So let's talk about the important features of the volcano. First of all, I'm going to use some fun colors here because my volcano is unique just like everyone else's. So here I'm going to draw, let's say I'm going to have more of a caldera. So instead of that shape like a cone, I'm going to have more of a caldera today as my volcano. So not too tall. This could also be considered a shield volcano, but let's use our imagination, right? So you can draw your volcano in any way you want. And so the first feature that we want to point out is the magma chamber. Do we remember talking about that magma chamber? It's also called the magma house. So I'm going to draw my magma house with this cool red. Kind of looks like fiery magma, right? So you can draw however big you want your magma chamber, whatever shape you want your magma chamber to look like. But here's my magma chamber. And then how does the magma go to the surface of to the vent or the area where it comes out as lava? What is that thing called right here that brings the magma to the top? Does anyone remember? You can
shout out if you remember, and you can shout out the answer.
Conduit.
Yeah. Good job. Conduit.
Tunnel. Tunnel is another word we can use for that, maybe.
Tunnel, yeah. I like to call it the magma elevator too. So here's my magma elevator or my conduit. So what is this where the magma comes to the surface of the earth? What was that called? Does anyone remember?
Vent.
Vent, good job. So this is my vent, and I'm just gonna draw kind of a line first. So here's my vent, here's my volcanic conduit, here's the magma chamber, and within it is my magma. So I'm gonna write out magma. It's a little harder than I thought it would be. Here we go. Magma. And let's say this magma has lots of bubbles. These are going to be my bubbles. I'm going to make this a really explosive eruption. So this, hopefully everyone's kind of drawing their own unique volcano right now. And you can add as many bubbles as you want, as many crystals as you want.
So it's bubbles, crystals, and liquid magma.
Exactly. That's what makes up magma. So my crystals are going to be this cool blue color. And you can draw crystals in any shape, but to distinguish them from bubbles, I'm going to draw them like elongate, long crystals or minerals.
And if you're using the worksheet, you might just use different shapes. I think my X's are my crystals and my O's are my bubbles. And I'll probably show liquid with a squiggly.
Yeah. Here my liquid is just going to be the empty space surrounding the bubble.
Oh, gotcha.
Or you can do it however way you want. So we're also going to draw those crystals and bubbles going up the volcanic conduit because it's going to erupt, right? So here's more bubbles. And mine's going to be a really explosive eruption. So what happens if I have a lot of bubbles and a lot of crystals? Is it going to be an explosive eruption or a non-explosive eruption?
Will it be like the soda bottle or like the syrup? Do you know, Colin? Do you want to shout out an answer? Oh, I'll let you unmute. I think we're hitting it at the same time.
Explosive!
Exactly. So I'm going to draw my big eruption cloud. Oh, I went into the words there. So this is my big eruption cloud. And I'm going to draw a pyroclastic flow going down this side and a pyroclastic flow going down this side, kind of similar to what happened at Long Valley, right? Where we had this big eruption cloud and then it collapsed down in all directions around the volcano. So here's my eruption cloud. So let's say some people might put a lava flow in. Let's just have fun with this. And I'm going to do an eruption cloud and a lava flow. Why not, right? This is my unique volcano. So here's my cool lava flow. This might happen, I might get a lava flow a few hundred years after this big explosive eruption. So let's pretend that this lava flow came in a few years after this really explosive eruption, which actually happened at Long Valley that I didn't have time to really get into. But if you want to learn more, I'm happy to talk more about the rest of the Long Valley caldera history. So, okay. So has everyone drawn their volcano or feels good about their volcano? Okay. So I'm going to get my text box and I'm going to put, so these different features of the volcano, let's start with magma. So we describe magma based on how many crystals, how many bubbles it has within it, right? So let's relate to magma and let's answer the question of how would you describe yourself? So for me, we can write into our areas here. Me, how would I describe myself? I'm going to say that I'm happy, I'm energetic, and I'm adventurous. Okay. You can put as many things as you want. And it's kind of hard to see it, but we can use our imagination. Actually, I'll put a background behind it. There we go. Okay, so that's my magma. Is everyone ready to move to the next feature? Yeah? Okay. So let's talk about the magma chamber itself. So let me move this. So we talked about magma, let's talk about the magma chamber. So the question for us is, where do you call home, or where are you rooted? So for me, I live in Bishop, California. So I'm rooted, my magma chamber, my magma house is in Bishop, California. Okay. Underline that so it sticks out a little. Okay. Are we ready to move to the next feature? Yeah? Okay, so the next feature, let's do the magma elevator, which was called the conduit. So conduit is spelled C-O-N-D-U-I-T, conduit. And the question we're going to ask ourselves here is what or who lifts you up or inspires you? Just like how magma is lifted up through the crust via the magma elevator, the conduit, what lifts us up and what or who inspires us? So for me, I'm going to put my family, my friends, and teaching others about the natural world. Because that's one of my favorite things that just makes me so happy and inspires me. Oops. Okay, so I'll give everyone a little bit of time. So is everyone ready to move to the next feature? Yeah, cool. So the next feature, we're gonna do the vent, or the area that allows the eruption to happen. It exposes the magma to the surface, which forms lava or that tephra that we talked about. So for this question, for the vent, how do you blow off steam? Or how do you relax? What do you like to do to blow off steam and relax? So for me, I'm gonna say I like to trail run. That helps me relax. I like to sit by an alpine lake and read a book. That helps me relax a lot. So what helps you blow off steam or relax? So I'm going to put that under here. Okay, are you ready for the next feature? Okay, let's do it. So the next one we're going to do is the lava flow or the pyroclastic flow. So here I drew both, but I'm going to pick to talk about the pyroclastic flow. And the question here that we're going to ask ourselves is, what's your favorite way to move or exercise? So with lava flows, we remembered that they move slowly like maple syrup. And then with pyroclastic flows, they're explosive and they move very quickly like that soda demonstration. So what's your favorite way to move or exercise? So I'm going to say my favorite way to move is with skis on my feet. I love to go skiing. Or I love climbing up mountains. Okay. That's the way I like to move. Now the very last one is the tephra. So if we remember, tephra comes from explosive eruptions, and it's anywhere from ash to rock fragments that are blown up into that eruption cloud and also incorporated within the pyroclastic flow. But tephra, the question we're going to ask that one is how do you contribute to your community? So how do you contribute to your community? That's kind of a harder question to ask. For me, I'm going to say that I contribute by providing educational programs to the public to educate and inspire them about the natural world. You could also say something like, you contribute to your community by being a happy person and smiling at everyone you see.
Or asking good questions.
That's a really good one. Asking good questions.
Sharing with others.
Sharing with others. Yeah.
Telling jokes. Maybe you're a funny person and you make people laugh.
Yes, I like that one. Being silly, that's also one thing I love to do. So that could contribute to our community too.
Or maybe you're a helper and you're someone that likes to help out your brother, sister, mom, or dad.
Mm-hmm. All right. So this is my unique volcano. Would anyone like to share their unique volcano?
Yeah. Go for it, Tor. It's Tori, right? All right, Clinton, do you guys want to unmute yourself and share first, and then we'll move on to Jennifer?
Yeah. Okay.
Great.
So.
Oh, cool. That's awesome. I like the colors too. There's a lot of bubbles in there. So is that an explosive eruption? It looks like it. Yeah. Awesome. That's a great.
Would you like to share any of your features with us? You don't have to.
I'd like to share a couple.
Okay, great.
So the people who really lift me are like my parents and teachers and my friends.
Awesome.
Teachers.
Very cool.
Yeah, that's great. Thank you for sharing.
And how do you like to blow off steam?
I usually take deep breaths, read or listen to music.
Very cool. All good strategies.
Yeah.
I could see a volcano taking some deep breaths to cool down.
Relax. To calm down a little bit. Yeah.
Thank you for sharing. Jennifer, did your little girl want to share? I see she has a nice volcano drawn too.
This is Addison. Go ahead.
Hi, Addison.
Hi, Addison. Wow. Look at that.
You want to tell me about it? Samson. Do you want to tell them about it? It's okay. You can be shy. Do you want me to read some of your words? Her lava flow is she said she likes to run and do yoga with mommy and dancing.
Awesome.
All right.
Nice one.
Thank you for sharing.
Sorry. Brother thinks it's a tiger. That's how he lets off his steam. He roars out.
We're all unique. I love it.
Oh, God.
Lori, did you want to share yours? I saw a thumbs up.
Mm-hmm.
Or maybe she was just liking somebody else's.
Oh,
Maybe.
yeah, everybody else's.
Okay.
Would
Does
anyone?
anybody else want to share? If not, no pressure.
Yeah.
I don't have a cool volcano. I just use the worksheet.
Cool.
But I guess I'll just share my conduit or what lifts me up. I really liked comparing myself to a volcano. I think it'll help me better connect with volcanoes in the future. I feel lifted up by vast open spaces. this area has really helped me to relax in that way. And kids, because they have the best questions and say the smartest things. A good story, and loved ones.
That's really great. The open spaces. I love that. I can relate.
As I get older, I notice I feel claustrophobic when in crowded spaces.
Yeah. Well, we live in the right area then. All right.
All right. Well, I guess that wraps everything up for us. And I want to thank you all for being here and for participating. Molly, a huge, huge thank you. I'm going to give you an applause as well. That was fantastic. Thank you so much. I've personally have been wanting to learn much more about this for a long time, so I really appreciate it. You did a fantastic job. And thanks for helping us relate and connect to volcanoes and appreciate both their danger, but also their positive impacts. So really, really thankful for all the time and energy you put into this.
Thank you. And with the resource list that we'll pass around, I'll include my email in there. So if you have any other questions or want to learn more about anything, feel free to reach out to me.
All right. Awesome. Thanks so much. We'll be sending out that follow-up email shortly. And then, I'll include your email in that follow-up email, Molly.
Perfect.
Okay, awesome. Well, thank you all for joining us. It was great to see you all virtually. And keep your eyes open if we have other virtual opportunities coming up in the future. We'd love to see you again.
We will.
Thank you for coming. This was so much fun.
All right. Have a great day, everybody.
Okay, bye, guys.
Thank you. Thank you. Bravo.
Thank you, Samson. Thank you.
Thank you.
Thank you.
The volcanoes, they're my favorite kind. They're my favorite kind of mountain. Me too.
Aww.
Thank you. That's
I
great.
didn't know this whole time. I mean, I knew I was skiing on at Mammoth Mountain. I didn't realize Red Cone was a mountain too.
Yeah. There's a lot of volcanoes in this area.
Colin, I might be with you. Apparently, I like skiing on volcanoes. All right. See you guys. Take care.